our next keynote speaker, that is Björn Nyberg. He is a researcher at the University of Bergen, where he works on the interface between geomatics and sedimentology in order to understand the changing natural environment due to climate change, sea level rise, and the Anthropocene. Björn, he applies data analytics in 3 key areas. Firstly, to understand the spatial and temporal evolution of sedimentary systems in the Anthropocene. Secondly, to predict the impact of a changing environment on our ecosystems and human livelihoods. And lastly, to develop remote sensing methods for characterizing modern sedimentary systems. And I will give the word to you, Björn.
Right, thank you. Hopefully everyone can hear me. I will share my screen here as well. Perhaps get rid of me here in the corner. And to the start. Right, so hopefully everyone can see this.
Good.
Yeah, I hope that ribbon will eventually disappear. But yeah, thank you for that introduction. And well, first and foremost, I'd just like to say that I'm very excited to be invited here. And I think this initiative is something really, really exciting. And I hope that we'll have a good future in the coming years. So what I'm going to be talking about today is about quantifying architectural elements of modern sedimentary systems, and really some of the work that I've been doing around that topic and where I see some of the directions going within this field then. Sorry, I just wanted this ribbon to disappear. Oh, there we go, hide it. Okay, perfect. So I'm going to try to keep this presentation as simple as possible. And what I really want to do is portray 3 main objectives or aims. And the first of that is to really talk about the broader applicability and importance of sedimentology in addressing 21st century challenges beyond perhaps the traditional hydrocarbon industry. Then I want to talk about some of the quantitative methods in where to find modern depositional systems for understanding sedimentary processes and their deposits. And then lastly, I want to talk about different methods to map and analyze the geometry and topology that we see within those different depositional environments, as well as some of the limitations and future potential that we can go towards. So having said that, what is the importance of sedimentology in general? I mean, sedimentology has traditionally been focused on characterizing reservoirs for hydrocarbon, and more recently towards CO2 sequestration, as well as, finding suitable regions for water aquifers. But sedimentary systems are also very essential for human livelihoods and the interactions between sedimentary systems and how that impacts our agriculture and different ecosystems and biodiversities. And something like 45% of the world's population today live in an active sedimentary basin. And then thirdly, understanding the behavior of sedimentary systems and our knowledge of how they change through time, I think at least can help us reduce the vulnerability of communities to flooding and coastal storm surges in light of foreseeable sea level rise and climate change. Now, personally, I've also looked at some other issues related to sedimentology, and specifically the influence of sedimentary systems and plastic distribution. And this is some of the work that I've been doing with Peter Harris and colleagues at Gridda in Arendal in Norway. And really, we're trying to understand how sedimentary systems transport, remobilize, and store plastics within sediments. And this has been, increasing, concern in recent years, where we have from the production of the first plastics in the 1950s to the present day, we have this exponential increase in the amount of plastic production, but also the amount of mismanaged plastic waste that we find as well. And our knowledge as sedimentologists can help with this. For example, in this top example here, hopefully you can see my mouse a little bit. We have a fluvial system that's transporting mismanaged plastic waste into this lagoon environment behind this barrier, sand barrier here, and trapping that in those mismanaged plastic waste or those microplastics within that region. The question is, what happens when we have, for example, sea level rise due to climate change? How will those remobilization of sediment perhaps reintroduce previously stored plastics back into our environment? And these are things that we're still trying to understand. But what we do know is that plastic pollution in our river systems impacts the entire world. And this is just a map showing the distribution of that. And it's absolutely amazing, the impact that we have. But we do see from this map, these green areas are these floodplain environments. And so these floodplain environments have a high concentration of mismanaged plastic waste. And certainly, again, our knowledge as sedimentologists and understanding how floodplains develop and deposit muds and silts has an important contribution in trying to understand what impact that has. We can also look at coastal change in different ecosystems. So how does our knowledge as sedimentologists and understanding of relative sea level rise relative to, subsidence, eustatic sea level, isostatic rebound impact different areas of our coast? And how can this help us solve some of these challenges that we face? And if you're interested a little bit more in this coastal change, I recommend that you tune into the talk by William Helen Hansen. I think it's tomorrow at the winter conference, where he'll explain a little bit more about that. But then also, how do sedimentary systems impact the ecosystem? This is some work that I've been doing with USGS and ESRI in the US, where rivers have an important impact in the bathymetry of our coastal regions, the turbidity, the amount of salinity in our water systems, and that impacts the ecosystems that we have in these regions. And again, all of these are, global challenges that we face and are goals that we are trying to address, for example, in these UN SDG goals for 2030. So that's just a little bit of a broader overview to keep in mind in the, application of sedimentology. Yeah. Can see if I can hide this again. Okay, perfect. So typically with sedimentological observations, what we're trying to understand is the sedimentary processes and their products of deposition, and then trying to relate how those will, change with time. And we can look at this from different scales of observations, whether it be from the bed form, the individual, sedimentary structures that are developing through time, to the bar form size, the individual mid-channel bars, for example, all the way up to how this connects into the basin scale. And all of these different scales have an interaction between those different scales. And it's important to understand how geometrically and topologically those are related to one another. And that geometry of a sand body element is what I refer to as an architectural element. And this has developed from Mile 1985. But essentially, in order to understand these 3D geometries of a basin infill, we really need to understand both the modern perspective, how it looks like in the plan form perspective, and from ancient observations, how it looks in time. And that can help us then constrain these processes and how they will change in time. Now, for this presentation, what I'll be focusing more towards is how to quantify and characterize modern sedimentary systems, and how you can apply those to your ancient outcrop. So having said that, how do we find a modern deposition environment? Well, I would say that you have essentially 4 steps. The first is to select a sedimentary system that is, analogous to your ancient environment that you're trying to understand. Map and digitize that modern sedimentary system so we can start to describe the different geometries that we have within that environment. Then extract that geometrical and topological information that we have from that, those mapped features. And 4, to analyze and interpret that data and how we then can incorporate that geometrical information in either the subsurface or trying to predict into the future. So going through those 4 steps, sorry. The first is finding a sedimentary system. And what can really help here is just first and foremost looking at where we find modern sedimentary basins. So these modern sedimentary basins are those regions that are undergoing subsidence, therefore creating accommodation space, and are therefore have preservation potential and are analogous to the past. And this is some work that I have previously done highlighting the extent of these sedimentary basins by their main or primary tectonic regime that are influencing these different sedimentary basins. And we can also look at the control or the climate control of those different settings as well. So this can help us narrow down, a modern example that is in a extensional basin of an arid climate with this type of precipitation, etc. And what's so, if we want to quantify, what's so important here as well is that these sedimentary basins represent only around 16% of the world's land surface. So that, significantly reduces the amount of area of the world that we actually have to analyze. Now we can also look at, how these influence submarine fans as well. The relationship between the drainage area and the submarine fans. And this is the global source to sink database that we produce. So the dark regions here is the drainage area, and the light regions here are the submarine fans. So you have that information too to help us constrain where we find different modern sedimentary basins. But anyways, once you find a sedimentary basin or sedimentary system that is within, analogous to your ancient environment, the next step is to map and digitize those depositional elements that you find within that sedimentary system. And this is an example from Australia in the Gulf of Carpentaria of the Mitchell Delta, which is a forced regressive deltaic system. And this is some work that has been done by Rachel Nansen, who was formerly at ASP at the University of Adelaide. But this provides us, or what they have done here is gone into the field, ground controlled where these different depositional environments are, and then use satellite imagery to help to constrain these sand body elements that we find in here then. And this mapping can either, involve manual, automated, or semi-automated approach using standard GIS software. And then after that, what we want to get out really is what is the geometry and topological information from these modern sedimentary systems, and how, once we get that information, we can then start to relate that to a particular ancient counterpart. So when I'm talking about geometry, I'm talking about measurable elements. So the orientation, area, what is the adjacency or the perimeter that one object is adjacent to another. So these are in terms of units and dimensions. Whereas topology is more about the relationship. What is the relation that this particular element is connected to this geometry and so forth. So that's what this diagram here shows, just a number of connecting elements between either fluvial depositional environment or architecture elements or wave influenced architecture elements. But all these tools that I mentioned here are open source GIS tools that I have developed over the past 4 or 5+ years. And they involve, almost, I think over 40 different algorithms at the moment to try to analyze different geometries and topological scenarios from modern depositional environments. And these are, again, all open source, and you can download them in QGIS just from the plugin menu here. And I have included, in addition, a QR code. So once this video is recorded, you can go back and scan that QR code and explore this or these tools for yourself. And there are a series of user guidelines and everything and workflows that I've developed as well in relation to these tools. So as an example, I want to just look at a distributive fluvial system. So for those who aren't familiar, a distributive fluvial system is defined as the deposit of a fluvial system, which in plan form displays a radial distributive channel pattern. And this is the definition provided by Adrian Hartley al. From the University of Aberdeen. But essentially what we see is from the source region, in the more proximal region, we see these braided to meandering fluvial systems, which are highly amalgamated, and we can see that within a vertical profile as well. From the medial, we start getting more meandering channels, which are separated by floodplain environments. And then once we get to the distal, we see very limited meandering channels, which is dominated by mainly floodplain environments, a highly drained area, and a lot of lacustrine environments. And the reason I choose this example for a fluvial system is simply because they dominate modern sedimentary basins and those types of sedimentary systems that we see in the stratigraphic record as well. So this is just an example quickly from South America, just off the Andes here in Argentina and parts of Bolivia. But essentially we see those trends or observations in the modern, where we see that proximal region, those amalgamated, braided to meandering sedimentary systems or fluvial systems. We see that medial area where we start getting predominantly meandering river systems with more floodplain material. And then in the distal region, it's almost dominated by floodplain environments. And again, there's a QR code there if you want to explore that in greater detail yourself. What's important, or what I want to stress here, is that a lot of these findings are based on observations rather than quantitative data. So here, for example, we have different types of DFS systems or distributed fluvial systems, whether it displays more of a braided or bifurcating system up here, or if we get more to the single and sinuous types of systems. And this is, hypothesized to relate to relative discharge and sediment supply and gradient and so forth. But there is really not a lot of quantitative data around that. Now, I had one master's student who looked at these, or a selective number of DFS systems around the world. I looked at how these rivers changed through time. So every single color here is one age, or one point in time where the river was at that particular location. And what she did for every one of those years then was to quantify how that river system has changed. So for example, here in the purple is 1 year, and the brown is where the point bar accumulations have occurred for that particular time slice then. And with those tools that I mentioned before, she's managed to extract a lot of quantitative data, which we haven't been able to previously do. And from that information—
4 minutes, Björn.
Okay, I'll hurry up. And from that information then, she's been able to quantify some of that data, how sediment supply versus discharge are related to each other, or channel slope versus discharge. So these are some ways that we can start to integrate that. But there is that quantitative knowledge gap. Yeah, so I'll quickly go through this now, but one of the directions that we have been going to is the Google Earth engine, and how that can help us solve in mapping on a global scale some of these challenges. And the good thing about Google Earth is it's integrated directly into Tensorflow, and Tensorflow is a machine learning algorithm, also developed by Google. But the nice thing is it's directly integrated into the Google Earth environment, so we can have that seamless interaction. So, yeah, I won't go into too much detail here, but essentially we do a fully convolutional neural network, basically a machine learning algorithm, to get an input image. Here's a dog, and then trying to define where that dog is then in that photo. And we do that instead for fluvial systems. Is this a meandering, or is this a braided system, essentially? And the initial results are very promising. So here we have the initial input images. Here we have the true mask, what we classify as true. And here we have the prediction of those architectural elements. And we started with fluvial systems, and the plan is to expand that to more complex sedimentary systems in the future. That's a work in progress, so stay tuned. So yeah, just to quickly summarize then, the main points: I think sedimentology has a broader application that we need to consider. 2, there has been workflows and tools developed for characterizing deposition environments. And these GIS plugins are open source and a community effort, so you're more than welcome to help contribute to that. And then thirdly, there still remains significant work in mapping the architectural elements or the geometries on a global and quantitative scale, which is really important to try to understand how some of these processes are changing in different types of environments. And ultimately, this will help us constrain, the architectural geometry and basin infill patterns and how to constrain and test numerical modeling. So these are some of the references that I've used. You can look back at them later. And yes, thank you.
No, thank you, Björn. That was really fascinating, extremely interesting, and a really important subject, since we should broaden our perspective, I think, on the applicability of sedimentology to other fields than just petroleum, and this is a really good example. That was nice to see. We are ready for any questions that might pop up here in the chat. Until then, I have a few. Firstly, I was wondering, in this plastic pollution that you talked about, whether you also include mineralogy as a parameter here.
Mineralogy? No, we do not. I mean, this plastic pollution is based off basically floating plastic that is detected around the world in different reservoirs as control points, and then based on population density and the amount of plastic that has been reported to be produced in different areas. And then connecting that with river systems to predict just where it most likely will end up entering.
Makes sense. There is one question now from Amanda. She says, how much did you find your quantitative data match the models of the river systems?
Are you talking in terms of the machine learning there, or? At the moment, I mean, with the machine learning, we have found, at least for a regional scale, that the machine learning has matched pretty well to the model that we have built, but we still have to test it on more of a global scale. Yeah.
She added here the measured parameters, for example, the channel width.
I mean, how that measures? Oh, okay, I see what you're saying. Yeah, no, I mean, they are pretty good. So the actual channel width that we measure from a manually interpreted example versus the machine learning automated example are very, very good. Yeah.
Thank you. And a question from Lina. In your opinion, what would be the role of the sedimentologist in mapping out the various sedimentary systems now that machine learning shows promising results?
I mean, machine learning is good at pattern recognition. So that is to say that we see this pattern, feed me 5,000 examples of this type of pattern, and this is that type of a sedimentary system. But what we really need to, or the sedimentologist role, is to understand what that pattern means in terms of the sedimentary processes that are involved and what sort of implications that has. So that's the role that I see between those two.
Interesting. And a question from Tor. In your fluvial example, you have relative time of the meandering system. Can you use that to predict timescales of meander belts and/or larger sand bodies in the stratigraphy?
Yes, I believe that you can. I mean, you have basically, I mean, I've only shown there one time slice, but we do have 40 years of time slice of these meandering river systems. So I think you can definitely use that to predict how that would look in stratigraphy. I haven't done too much of that, but I think you need to perhaps stay tuned to Sultan, who I think is presenting later, because he does a lot of numerical modeling around that. So I'm hoping he will show some examples there.
Thank you. And I think we have time for one last question here before moving on.
Okay.
From Marcelo, when mapping a system in 2D, how do you think the results relate to the 3D volumes, including the subsurface?
3D volumes is always difficult. You need to, have that in your back mind, that, the modern, what you're observing is not necessarily what is going to be preserved in terms of volume and proportions. Again, I think that's where we have to use, our sedimentological knowledge to relate those, because it'll depend a lot on terms of, the amount of subsidence and the amount of sediment that's being supplied to a particular region.
Thank you for that answer. And I know it's 25, but Mikael has a good question here. So if you can give a quick answer to that one.
Okay.
When we look at most of these shoreline reconstructions and analysis, we tend to miss the immediate link with the adjacent subaqueous shelf portion of the system. Do you have an idea on how we could get and integrate more data on those parts, perhaps remote sensing?
Yeah, so that's quite interesting. I mean, there has been a lot of work looking at more multispectral satellite imagery, which can penetrate further into the water column. So we can measure bathymetry down to around 20 meters. So there is potential to get a little bit of that subaqueous knowledge as well from satellite imagery as well.
Thank you very much. Only 1 minute past time. Very interesting presentations here and good questions. If you have more questions, I guess you can ask Björn directly or ask in the chat, then you can reply there.
Yeah, I mean, send me an email, Twitter, whatever. I'll try my best.
I'm looking very much forward to follow your work further on now.